Okay, so we're doing 5.3b today, and this is example 1. We're taking the integral from 0 to 1/2 of 1 over the square root of 1 minus x squared. So on Monday, we learned...
Mr. Couch said on Monday we learned.
Sorry, I didn't hear. I didn't know I was funny. Thank you. I mean, apparently I'm so hilarious I can say anything and make people laugh at this point.
Wait, do we have 5.3 annuals?
Yeah, I'm very sorry, but yes, we did. It was a while ago, though. Yeah. Okay, so on Monday we learned a snazzy way to figure out area without a calculator, right? That avoided limit as n goes to infinity of the sum I equal 1 to n, yada yada. Okay, so just what was that method? How do we find area without a calculator? Take the antiderivative of the function, then plug in the two numbers and subtract, right? So that was the fundamental theorem of calculus part 2. So what we have to do here is take the antiderivative of this mess. That's a little bit tricky, but it's still just taking the antiderivative of that. Okay, now somebody, second bell, said that it would be the ln of the square root of 1 minus x squared. That's not exactly correct, but do you see why somebody would have thought that? Because the antiderivative of 1 over x is the ln of x. That's true. So it kind of seems like the antiderivative of this should be that. So this is sort of right, but let me take the derivative of it to show you why it's not completely right. So if I take the derivative of this, you would have 1 over 1 minus square root of 1 minus x squared. But then you would have to times by the derivative of this from chain rule, right? So that would be 1/2 times 1 minus x squared to the negative 1/2 times negative 2x. It's actually a double chain rule. Don't think about this too much. Just know that the correct derivative of this is this. So the antiderivative of all of this would be that. So the antiderivative of just that part of it is not that. Everybody okay? This was good thinking, because ln sometimes is involved with 1 over something. It's just not, in this question, the right answer. Okay, so what is the antiderivative of this mess? Yes.
Is it 1 minus x squared to the negative 1/2?
You could rewrite that
Oh, yeah.
as 1 minus x squared to the negative 1/2. But that's not the antiderivative. Good thinking, though. So they didn't remember second bell either. That's okay. Don't feel bad. The antiderivative of this is inverse sine. Yeah. I mean, we had it just one day, and you memorized it maybe for one test, but you haven't seen it in a while. So the derivative of inverse sine is that, so that means the antiderivative of that is inverse sine. Okay, so then after you take the antiderivative, you have to plug in 1/2 and plug in 0 and subtract. Oh, don't forget, we're supposed to put plus c, right? But the fundamental theorem says any antiderivative will work. So I usually put plus 0 down. That's what I wrote, quote unquote. I wrote plus 0, right? Okay, so then you have to plug in 1/2 and plug in 0 and subtract. So we're going to take the inverse sine of 1/2 minus the inverse sine of 0. Okay, so now the trig is a little bit tricky. The inverse sine of 1/2 is, apparently this is a non-calculator problem, right? Otherwise we'd just be math 9ing this thing. So we better figure out the inverse sine of 1/2 without a calculator as well. So the inverse sine of 1/2 is asking the question, what angle has a sine that is 1/2? Okay, so looking at the unit circle, that would be this angle. The sine is 1/2 on the unit circle when the y value is 1/2. So then maybe that triggers your memory that that's supposed to be √3/2 if the second number is 1/2. And that angle is pi/6. You probably knew it was either pi/3 or pi/6, but sometimes you get those mixed up. It's pi/6. That's this one. Okay, so the angle that has a sine of 1/2 is pi/6. Then that second question is, what angle has a sine of 0? So that means that the second number needs to be 0 here on the unit circle. And of course that happens at the point 1, 0, which of course is this angle, the 0 radian angle. So the angle that has a sine of 0 is 0. So that's pi/6, that's 0, then we gotta subtract those. So the final answer is pi/6. Yeah.
Wouldn't it also be 5/6?
So inverse sine, we don't want there to be a lot of answers to that question. Because you're right. One possible answer to this, if I ask the question, what angle has a sine of 1/2? There's a lot of answers to that question. Pi/6, 5 pi/6, and then 11 pi/6, or sorry, 13 pi/6 also has a, and then you could add another 2 pi, and 25 pi/6, et cetera, et cetera. So there's a lot of possible answers to the question, what angle has a sine of 1/2? So because of that, we've decided that this symbol here is only going to give the answer between -pi/2 and pi/2. So the range of inverse sine is this. And that's why 5 pi/6 isn't the correct answer to that question. Just because the mathematics community decided that the one they wanted was the pi/6 rather than the 5 pi/6. Great question. Does that totally make sense now? Yeah. Yes, Clark?
So is the range of cosine -1, 0 to pi?
Yes. Yeah, 0 to pi. And inverse tangent is -pi/2 to pi/2 also. Good. All right, everybody good now with the pi/6? Sure? All right, so for example 2, we're going to have s of t equal t squared plus 5. T is going to be given in seconds, and s is going to be in meters. And for part A, the question is, find the average rate of change of the position on the interval 2, 5. Okay, so average rate of change is a question from chapter 2. So I'm not saying that to make you feel like you're supposed to remember it. I'm just reminding you that it's from a long time ago, so maybe you don't remember. So how do you find average rate of change? It's just f of b minus f of a all over b minus a. It's just the slope formula. But we're calling it average rate of change because it's not on a straight line. Okay, so in this case, we're trying to find the average rate of change of the position. So it's going to be s of b minus s of a all over b minus a. So in this case, the b and the a are 5 and 2. So it's going to be s of 5 minus s of 2 all over 5 minus 2. So s of 5 is pretty easy to figure out. You just plug it in here. 5 squared is 25, plus 5 is 30. So that just means when the time is 5, this particle is at the position 30 meters. So there's the number line up here. And it's at 30 meters at the time 5. And then you plug 2 into the position function. That comes out to 9. So that means at the time 2 seconds, it was at the position 9 meters. So then if you subtract those, that gives you 21 meters. And that's called the displacement, right? It was at 9, now it's at 30, and those are 21 apart. So the displacement is 21 meters. And then that happened in 3 seconds. So you would take the 21 divided by the 3, and then you divide that out, and you get 7 meters per second. So the average rate of change of the position is 7 meters per second. Okay, now for part B, we're going to find the average velocity on the time interval 2, 5. Now this is a chapter 5 problem, because it's talking about the average of a function. What's the formula for the average of a function? 1 over b minus a times the integral of from a to b of f of x dx, right? Okay, so the formula we're going to use is this one. That's just the general formula for the average of any function f on the interval ab. So of course, this function, the interval is 2, 5. So the b and the a are going to be 2 and 5. Okay, now what are we trying to find the average of? We're trying to find the average of the velocity. So what function should we put here? The velocity function, right? Yeah, that's how we're going to find it. Good. So if we're trying to find the average of the velocity, then this f of x needs to be the velocity. So yeah, how do we find the velocity, Matt? Yeah, we just take the derivative of the s function they gave us, right? And that's 2t. So then that's what we're going to put there. So then from there, this would be 1/3. Then how do you calculate this integral? How do you calculate any integral? You can graph it and try to find the area, right? But what's the new way to do it? Take the antiderivative of this, right? Okay, so the antiderivative is t squared plus c. Remember the fundamental theorem says you can put plus anything you want. What do you think we should put plus here? 5. We know it's plus 5, right? So we might as well use the correct c. It would be fine to put plus 0 there. Nothing wrong with that. But I'm just emphasizing that any antiderivative will work. Okay, now this is kind of weird. We We started with the position function, then we took the derivative of it, and then we took the antiderivative of it. It seems like we're going in circles, right? But we're not going in circles. This is a particle question, and it's just in a straight line. That's supposed to be funny. I know it's not funny, but. Okay, but we're not going in circles because the reason we did this derivative is because we needed to find the velocity formula so that we could plug it into here because we're finding the average of the velocity. And then it just kind of happens that the way to calculate that is to find the antiderivative. So it's a derivative for a specific reason and an antiderivative for a specific reason. Okay, so then you plug in 5 and 2 and subtract. So this is going to be 1/3. When you plug 5 in, you get 30. When you plug 2 in, you get 9. And then that's 1/3 times 21. And so then that comes out to 7. So what was the label on velocity? What is the label on velocity? Meters per second. And we were finding the average of all those velocities, right? So then the label on the average should be meters per second. So we were finding the label on velocity is meters per second. We are finding the average of all those, so that's why this is in meters per second. Okay, now it is not a coincidence that this answer is the same as this answer. It's totally not a coincidence. It's even the same work right here, right? That's identical to that. So the reason it's not a coincidence is if you have the rate of change of the position, that's the same thing as the velocity. So if you're finding the average of the rate of change of the position, you're actually finding the average of the velocity. So these questions are the same question, just worded in a different way. And this is the chapter 2 way to do the problem. And this is the chapter 5 way to do the problem. But it's the same thing. So it doesn't matter which method you use. So what the purpose of example 2 was to take chapter 2 and chapter 5 and connect them in your brain. See that there's one way to do it and another way to do it, and they're really the same. Is everybody okay with that?
I have a question.
Yeah.
You said the C to be negative +5.
Sure.
So how would, if it wasn't, how would that change?
So let's say I picked +1. So 25 plus 1 is 26. 4 plus 1 is 5, and 26 minus 5 is 21. Yes. So that's why it doesn't matter, because you're going to get the same final answer. Because whatever this is, it's going to get added and then subtracted. And so really you're just taking that number.
That's all.
Good. Yes.
So the fact that we took the derivative and then we took the antiderivative, it was just a coincidence, like it doesn't happen every time.
No, it wasn't a coincidence.
Yeah.
I kind of spun it as that, temporarily, so that you would think about this in a chapter 5 way and think about this in a chapter 2 way. But certainly, this is S of 5 minus S of 2, according to the fundamental theorem. We learned that Monday, that this is that. So then this corresponds to that. So it's the same exact thing, just from a different angle, a different perspective.
Okay.
Good. Okay, you guys are doing good. Got one more problem here for you. So this is example 3. We're going to find the area from -1 to 2 of x minus 2 times the absolute value of 1 minus x dx. Okay, so when you calculate area in the new fancy way, what do you have to do first? Take the antiderivative, right? So we need to take the antiderivative of this function here. Now that's going to be tough because we don't know how to take the antiderivative of an absolute value. We haven't had a derivative that popped out an absolute value, so we're not going to have an absolute value antiderivative. So in order to figure out this question, our first step is to get rid of the absolute value sign. Because then we'll be able to deal with the antiderivative. We can't deal with the antiderivative if there's an absolute value sign in it, so we're going to get rid of it. Okay, so let's say that this mess that's inside the absolute value signs, let's say that that mess was positive. What would the absolute value signs do to that positive number? Absolutely nothing, right? Because absolute value just takes a positive number and spits it back to you. So I'm going to figure out when that mess is positive. Because when that mess is positive, I don't even need these straight lines around it. Okay, so I'm going to go off to the side and calculate when that mess is positive. So I'm going to subtract 1 from both sides. And then divide by -1. When you divide both sides of an inequality by a negative, it switches the direction, right? So that's why it's less than 1. So we just found out when x is less than 1, this mess here is a positive number, which makes sense, right? Because when x is a half, 1 minus a half is going to be a positive number. Or when x is -3, 1 minus -3 ends up being 4, positive number. So when x is less than 1, that's positive. Okay, so that means that when this mess, when you plug in an x that's less than 1, that mess is going to go positive, and thus we're not going to need the absolute value signs. Okay, so what I'm going to do is I'm going to split this area up into 2 separate areas. I'm going to do the area from -1 to 1 separate from the area from 1 to 2. That's going to work out just fine, right? Because if I do the area from -1 to 1 and then the area from 1 to 2, that'll give me the entire area from -1 to 2. So the reason I split it up like that is because from -1 to 1, that mess is positive. Because all of those x's are less than 1. So for this part, I don't even need the absolute value signs. I can just drop them. So why are the absolute value signs unnecessary? Because that number is positive, and the absolute value signs wouldn't change it or do anything to it. So that's why I was just like allowed to basically ignore them. Okay, but from 1 to 2, that mess is going to be negative. So I can't get away with just getting rid of the absolute value signs. Okay, so what does absolute value do to a negative number? It just makes it positive, right? So what we need is a process that takes a negative number and makes it positive that's not absolute value. Okay, good. The problem is squaring will get rid of the negative, but it'll also give you a different number.
What did you square by?
Both whats?
Both functions.
Yeah, the problem is we don't have an equal sign
Okay.
here, so we can't square both sides. We've only got one side. We've only got one number. So I like what you're saying. If I squared that number, that would make it positive, but it would also make it a positive different number. Okay. So how can I take a negative number and make it positive and not change the number? Multiply it by -1, right? If I take -3 and multiply it by -1, then that gives me +3, just like absolute value would do, right? So that's what I'm going to do. I'm going to recopy this. And then I'm going to take this 1 minus x and multiply it by -1. Because that negative number times this -1 does the exact same thing as that negative number absolute value. Everybody okay? This is the most technically tricky thing we've done today. Algebraically tricky. Totally good? Okay, so now I'm going to do some simplifying. I'm going to distribute this -2 here. So that's x minus 2 plus 2x. So that would give me 3x minus 2. So I can do the integral from -1 to 1 of 3x minus 2 dx. Then I'm going to do something similar here. But if I have a -2 times a -1, that's basically +2. So then I can distribute a +2. So that would be -x plus 2. Everybody doing okay? Okay, so now I have to do antiderivative of this and plug in 1 and -1 and subtract. And then I need to do antiderivative of that and plug in 2 and 1 and subtract. So antiderivative of that is 3x squared over 2 minus 2x. That's from -1 to 1. And then this antiderivative is -x squared over 2 plus 2x from 1 to 2. Am I doing okay still? So now I got to plug in the numbers and subtract. So that's going to be 3/2 minus 2 minus, so I plugged in 1 and that's what I got. And then plug in -1. -1 squared is +1, so that's why that's still +3/2. But -1 times -2 is +2. So that bracket corresponds to this, right? Okay, then for the second integral, I get -4/2 plus 4 minus -1/2 plus 2. So then that is 1.5 minus 2 is negative a half. 3/2 plus 2 is, actually, this is going to be easier. That 3/2 minus that 3/2 goes away. So it's negative 2 minus 2, which is negative 4. Everybody okay? So this is negative 2 plus 2 plus 4, so that's 2. This is negative a half plus 2, so that's positive 1.5. So we have negative 4 plus a half, so we have negative 3.5. Everybody doing okay? Okay, so yesterday, Micah, this is the third grader, he was working on measuring some things. So he measured a pencil that was on his paper. He had to get out a ruler. And he was supposed to do centimeters and millimeters. Or sorry, and inches. Centimeters and inches. So he did the centimeters, and it came out really nice. It was like 6 centimeters. So he had 6 centimeters written down on his paper. Don't check the accuracy of my answers here. I don't remember what these numbers were. Okay, so then when he did inches, it was like 3 of the inches, but then it was past the inch mark, so there was 2 more marks, right? So he said 3 inches and 2 milliliters. Okay, now if I was not a math teacher, I would have looked at that and I would have said, milliliters, that's horribly wrong. What are you doing? But being the math teacher I am, I was like, well, where'd you get this 2 milliliters? And so, first of all, he said, well, when I'm in science class, we've been measuring like liquids. And so you got this like beaker thing, right? And on the side of it are the liters, the centiliters, right? And then there's 10 parts. And so he said, so if you have a little bit of extra height, then that's a milliliter. And I was like, that's awesome. But here's the problem. You weren't measuring the height of that liquid. You were measuring the volume of that liquid. So then I got out a gallon of milk, and I said, okay, here's a gallon of milk. But if I poured this gallon of milk into a different, thinner container, it would go up higher, right? So the volume is not only the height of the liquid, but it's also the amount of space that the liquid's taking up. And he was like, oh, yeah, we've talked about that. I just didn't understand that that's what we were measuring. I thought we were just measuring the height of the liquid. You can understand why, because you are just looking at a thing on the side that's the height of it, right? So then, because he wrote that down, I was able to talk about volume and stuff. Okay, then I said, okay, now let's go back to our centimeters. There's little marks in between the centimeters. How many of them are there? We counted them. There's 10. So each of them is 1/10 of a centimeter, right? So that's a millimeter. But this is inches. So how many marks are there? Oh, Dad, there's 16 of them. So this is 2/16, not 2/10. So we talked about volume, fractions, everything. Wow, that's awesome.